I'm Ken Davis, Mathematics Consultant with the Wisconsin Department of Public Instruction. I want to talk a little bit and give you a specific example of how we use visual representations in secondary mathematics. In secondary mathematics, it's not a lot different than what it is in elementary mathematics. We can start with concrete examples and start off with something very hands-on as far as looking at blocks. And in this case, we want to look at the patterns of how these blocks are growing. In our first figure, we start with 2 blocks, then we go to 4 blocks, then we go to 8, and then we go to 16. So that idea of looking at patterns with blocks in secondary isn't really that much different than it is of what we use when we look at elementary schools. What makes it more complex is how the blocks are growing. In this case, these blocks grow at an exponential rate. If we look at the next phase of this and we look at it pictorially, in this case we'll look at it in a table, we see that these cubes are growing, like I said, from 2 to 4 to 8 to 16. They're growing in an exponential fashion. And because they grow in this fashion, that makes it a little bit more complex than what we might look at growth as far as we would look at growth in an elementary setting. Another pictorial idea that we would introduce in secondary would be the idea of converting a table to a graph format. Again, it's still a different representation, but it represents the data in a slightly different way. And finally, in abstract, when we start looking at abstract in secondary, we move more away from working with numbers and we move more into working with symbols or variables, much more than what we do in elementary. The ideas or the concepts that we use in secondary don't differ a whole lot from what they do in elementary. Let's look at the concept of multiplication as it progresses from elementary to secondary level. In elementary, in mathematics, we look at multiplying 2 numbers together. We can look at that as arrays, we can look at it as number of sets, we can look at it in those ways. That idea of looking at multiplication that way doesn't change when we move into secondary. What changes is the things that we look at. Now, in mathematics, we now look at and we introduce this idea of variables. In this case, we're looking at multiplying x plus 2 times x minus 3. The concept of multiplication doesn't change. It's what we multiply changes. And then when we go into the even higher levels in mathematics in secondary, we're looking at changing the form of the way something could look. This is also done in elementary school. The slight difference is we look at it more using variables than what we do in using actual numbers. But the way we break down those numbers in elementary school, we may break it down into tens and ones. That idea doesn't change. It just modifies a little bit with the idea of looking at variables instead of just looking at numbers. Our task as teachers and students is to see how are these connected. And again, we can use the idea of concrete, pictorial, and abstract to get this done. Now, we've already done a quick look at concrete, pictorial, and abstract in elementary. We look at multiplying and we look at using base 10 blocks to do that. So if we were to multiply 10 times 15, we can look at it in this format using this area model idea to look at how we could multiply. Then that grows from that concrete model to our pictorial model where students might actually write with the numbers. Again, taking their idea of what they used when they were manipulating the blocks and then putting numbers in there and then also getting a different representation of it. And then finally that leads us to the abstract notion where the students would actually work with the numbers. Again, the thing I want to highlight here is that this idea of going concrete, pictorial, abstract doesn't change because we move from elementary mathematics to secondary mathematics. Before we begin and look at an area model for mathematics and what it may look like at algebra level, we need to model or come up with a model. And in this case, we're going to model a polynomial. And we're going to use blocks similar to the way that we use blocks in elementary. Our little red square would be a -1. Our yellow square would be a +1. Our longer rods would represent the variable x and -x. And then our squares would represent x squared and -x squared. So if we're looking at multiplying x plus 2 times x minus 3, using a concrete model, we can do something very similar to what we did with base 10 blocks. Across the top, we could lay our x minus 3, and along the sides, we lay in our x plus 2, and then we kind of fill in blocks to figure out what is the result of this by looking at the area that's bounded by the region. In a pictorial view, again, we're taking that same manipulatives that we use, except this time we're actually going to work a little bit more with the variables and the numbers, and we're going to get really the same thing, but a different version or a different view of what it looks like when we actually draw it out, because we can't draw all of those blocks. So we'll start using variables and numbers in that sense. And what this leads us to is this abstract idea, and this leads us to this FOIL method that a lot of people in algebra should be familiar with. I'm sure some people are having nightmares about having to do FOIL when they were back in Algebra 1 class. But this is how we can build to that FOIL method of multiplying two binomials together, looking at it concrete, pictorial, and then finally looking at the abstract version of it. For some students, it is quite necessary to look at multiplying these binomials in this fashion, because if we jump right to the abstract, sometimes it just doesn't make sense for a lot of students. They need to see and work with and manipulate the blocks, then draw a picture of it, which gives them a different representation, and then the abstract idea will make more sense for them. We can continue this idea when we look at this notion of something called completing the square, which we do in a lot of times in third year mathematics or in an Algebra 2 class, where we're going to change this polynomial, this x squared minus 4x minus 8, and we're going to make it look different, even though it's going to be the exact same thing. So if we were to represent x squared minus 4x minus 8 using our algebra tiles, it would look like this. So the big blue block is our x squared. We have 4 red x's, that makes them -4, and then we have 8 of the squares, the red squares, which makes that -8. Our task is going to be, we need to figure out what's missing in order to make this thing into a square. Thus, the reason why we call it completing the square. We're going to figure out, what can I put in that corner to make this thing a square? What blocks can I put in there that will complete this? And you can probably figure out that we could put in 4 yellow squares that would complete this. And they need to be positive. You might ask, well, why didn't we just put 4 red blocks in there? But if we do that, it doesn't match, because we have a negative times a negative, or red and red won't give us another red. It would actually give us a positive. So if we're going to add these 4 ones on to complete our shape, then we have to also add in 4 negative ones, because there's something about this polynomial. We can't add in 4 out of the blue, because that changes its value. Now, if we add in 4 positives and we add in 4 negatives, we don't change the value, because in essence, we've just added 0 to this, so we haven't really changed it. It might look like we've changed it, but in actuality, we haven't changed this thing at all. So now this is a representation of x squared minus 4x minus 8. It doesn't look like our original representation, but it does represent the same value. Now we can figure out what's bounded, or what bounds the regions of this, and then we can see this, that it's x minus 2, and then x minus 2 is what bounds this region. And then we have this -12 blocks that are kind of left over. So basically what we've just done is we've completed the square. We've rewritten the form of this polynomial. And in the next slide, I'll show you what that looks like in the end. So again, we can take something in this concrete format. We can manipulate blocks. We can move them around. We can rearrange them. The goal is to rearrange our blocks into a square. Then we can do a pictorial of what we did, or we can draw a picture of what we did, but we're not going to draw in all the blocks. We're going to use the variables and the numbers to represent what those blocks are meaning. And you can see there in the bottom right corner that I've added in my 4, and then because I added in my 4, I had to take off the 4. And then what this all means is, here's this abstract idea of what it means to complete the square. So we've changed this from x squared minus 4x minus 8, and we've changed it in the bottom, you'll see we've changed it to x minus 2 quantity squared minus 12, and thus we have completed the square, or we've rewritten this into what's called vertex form. Again, some students may struggle if we jump right to this abstract notion of completing the square without seeing it in a concrete format, being able to manipulate it, and then also to be able to draw a picture of it or a different representation of it. So just like we would do with elementary students, we could take secondary students through the same progression in a lot of cases so that they have a deeper understanding of what's going on when they look at something in an abstract form. So again, the most important thing that we have here when we use and connect mathematical representations is that students should learn to represent, discuss, and make connections among the mathematical ideas in multiple forms. This will help them to demonstrate a deeper understanding of the mathematics.